Hi, everybody. We'll continue these concepts of calculus, and we are now in chapter 3. And so we'll talk about differentiation and derivatives. We discussed the tangent, the slope of a tangent, the limits, combining both, and difference quotient formula. So different ideas that took us to the definition of a derivative, right? So now we take that and use it to come up with some derivative formulas. However, we need to look first into some rules of differentiation. So 3.1, although this says basic rules, it doesn't mean there are few rules. They're still basic in the way we apply them. However, there are many different rules, and as you will see. All right, so we'll start with the four rules. The first one is the derivative. We will put this notation dx. What does this mean? It means the derivative of f with respect to x at x, which means we differentiate with respect to x. That's the variable that is of interest. And sometimes, what does that mean? Let's say you have a function, and if this is the variable that is of interest, then we differentiate to that. If we have a motion, for example, and this is f of t, it's a position, how it changes per time, we may differentiate that with respect to t. So really, the variable we're interested in, that's the one we differentiate to, and how the function behaves with this variable is what's going to be of interest, right? So we'll see 3 examples. The notation, sometimes you may see write y prime or f prime. That's what it also means, this differentiation. In some occasions, you'll see dx, something like this. All right, so the derivative of a constant is 0. And what does that mean? For example, if you have a constant function, let's say this value of y is c. As you see here, the slope is 0. It's not changing. And that's what that derivative stands for, is the rate of change. This rate of change is not changing. And because of that, the derivative of this constant is 0. If this is f of x, f prime of x is 0, right? So that's to keep that in mind. So if you have a 28, f of x is 28, derivative of 28 is 0. It doesn't have x there. Pi square is 0. So we can't mix this constant with the multiple. So we will see that next. The power rule, number 2, the power rule here is the derivative of, let's say, x squared, which is a parabola. If you take a derivative of this one with respect to x, you will use the power rule. It's a 2, x 2 minus 1. There is something we don't talk about right now, but it is 1. This one comes from the derivative of x to x. So, but it's good to just know it as we move on. Right now, the formula is simple, but seeing it now will help you understand it. If you see later when you cannot use this, what do? So dx over dx is 1. Usually it's multiplied by dx over dx, which is 1. So it's just 2x, right? So for right now, for the power rule, this is how you're going to apply it. So for example, if it's just x, it's 1, 1 minus 1, x0 is 1. 8, 8 to x to 7th. If it's a fraction, 5 halves, so 5 halves, then here you do 5 halves minus 1, which is 5/2, right? So you see, it's kind of straightforward. To differentiate a function whose rule involves a radical, we first rewrite the radical using a fractional power. So let's say a square root of x, that's a simple one. Then you change it to x to 1/2, right? Then you apply the power rule on it. 1/2 minus 1, so 1/2, negative 1/2, right? And that becomes, you can leave it that way, or it becomes 1/2 x to 1/2, which is also 1/2 square root of x. So these are different forms of it, right? So let's see. The resulting expression can then be differentiated using the power rule. Right? The derivative of a constant multiple of a function. So this is not the derivative of a constant, so let's make sure we know that. If I have the derivative of 5 is 0, but now we're talking about the derivative of a multiple like 5x. 5 is multiplied with x, so what we do is we keep 5 to the side, based, you see on the rule, c times f, c outside, f inside, dx, dx, which is 5. Let's say d to 8, of course, if it's just 8, that's 0. But if I have d to 8x squared, right, that's 8 times the derivative of x squared, which is 8 times the derivative of x squared, which is the power rule, is 2x. So the answer is 16x, right? And here are some examples. So the 5 is a multiple. And it's set to the side until you do the derivative using the power rule, and you get 15x squared. If you have a square root, that becomes it becomes 1/2, right? So then you bring it here and it becomes a negative exponent. Then you do the derivative, which means the 3 is a multiple. It sits outside. Then you take the derivative of inside as using the power rule, and it gives you this answer. So here you do negative 3/2 minus 1, and you get that. So for the sum rule, and the sum rule, of course, here is the sum and the sum of the opposite, which is the difference, right? It's direct. It just says if you have to do the derivative, for example, of 5x cubed plus 3x squared plus 1, for example, of this polynomial. Let's change this one to -1, doesn't matter. If you have multiple terms added or subtracted, you can split them and do the derivative of each part. Then you just apply 5 is a multiple. The power rule says 3x squared. 3 is a multiple. X squared, the power rule says 2x. 1 is a constant, so it's 0. So we get 15x squared plus a 6x. So that's what the sum rule uses. So as you learn these things, you want to summarize in a separate sheet these rules. So when you do more problems, you kind of understand how they function and where they should be applied. So here are some examples, as I mentioned. So F is similar to the one I did, so you can pause the video and do this one. but I'll talk about number B here, or the second one, B. So if we have, just to distinguish, if this is t squared divided by 5, we should know that that's similar to t squared multiplied by 1/5. So that's what we want to understand. That's a 5 times 1 over t cubed. So if we see it this way, we will know how to put it in a form that is easy to differentiate. All right. So if we do it that way, then we can switch it now to when we take the derivative, we'll have a 2 times 1/5, and this is a 2 minus 1. Then this here, you see now it becomes a negative exponent, so we can do the power rule on it. So it becomes negative 15, 5 times negative 3, minus 1 will become negative 4, and that now becomes this form. And if you want to combine the two, so this is good or this is good. All right, so 2 problems from these 3.1, and more will be done in class. So similar way, when we see the product rule, you don't have to apply the product rule here, although we didn't do it yet, but just when we do that, don't mix it with multiple. The multiple one is easy, so we keep it easy. So if we want a derivative of this, negative 1/6 is a multiple, so we need the derivative of this here, which means we need a derivative of this minus the derivative of this one here, right? That's a power rule. Negative 6 minus 1 would be negative 7, and that's a 12x11. Then now this can be distributed inside. We give us 6 over 6, so x minus 7, and that gives us positive 12 divided by 6, which is a 2. All right, so this is that, or 2x11 plus 1 over x, this is 7. So if we want to rewrite without any negative exponents, we take that one. All right, this other question here is the demand. We've done different word problems like this, and we looked for equilibrium and different ideas. Now we'll connect them with this derivative idea. So we have a demand function for the luminar desk lamp is given by this P or f of x, where x is the quantity demanded in thousands and P is the unit price in dollars. So find the derivative, which means find the rate of change at x, any given x, to do the formula. So f prime of x is 0.1 times 2. X, you do 2 minus 1, which is 1. And 0.3x, and x will be 1 minus 1 will be 0. So, you do 1 minus 1, it'll be 0. So we're going to be skipping this part. If you have 6x, derivative is 6. All right, so negative 0.2x minus 0.3. That's that. What is the rate of change of the unit price in dollars per 1,000 lamp when the quantity demanded is 11,000? So this is something we talked about so many times now. When the model is given in thousands, right? And the quantity now in 11,000, that means X is taking 11, right? So that's something we've done multiple times now to understand how the models function and how to read them and how to interpret them and how to, look into the results and understand the results. And we did the graphs. So next discussion will be about these graphs. Okay. So F prime, the rate of change. So keep in mind, the question is about not the units, but the rate of change of the unit price. So the rate of change. So that's 11. And that should be negative 2.5. So what does that mean? It means it is decreasing at the rate of 2.5 per 1,000 lamps. So what does this mean? It means, you see it's a rate of change, it's negative. It means it is decreasing by a rate of 2.5 per 1,000 lamps. All right, so the last question, maybe we can call it. See, what is the unit price? The unit price, this one is the one that controls these prices. And so we will just do f of 11. So f of 11 is the first equation with 11 substituted. And we'll try this, and we should get 20.6, which is $20.60. So the major takeaway here we need to understand, and when we look for derivative, we are looking for some type of rate of change, right? Some type of slope, sometimes of something changing, and we get information from it. So like it looks like here for the 10,000 units, the unit price is decreasing by a rate of 2.5 per 1,000 lamps, right? All right, thank you.